All right, and welcome back to the second panel of the NDRI Science Symposium. This one is based around the NDRI degradation and contaminant studies. So we have another excellent lineup of researchers, and I would just like to acknowledge the time that the researchers have contributed to this symposium and ensuring that it is going to deliver value in terms of helping people understand the NDRI research and how we inform decommissioning decision making. The theme for this panel is what might happen if structures are left in the ocean. The facilitator for this session is someone who knows a lot more about data and science than I do. I am the only person without a doctor or a prof in front of my name contributing to this symposium. So Dr. Tom Cresswell from ANSTO is much better placed to facilitate this critical session on, as I said, around the degradation and contaminant studies. So with that in mind, I am going to hand across to Tom to facilitate this panel.
Thanks, Andrew. And it was a great session, the first session, so I really enjoyed that. And I think, again, there's some lots of segues for us to then discuss in this particular session on what happens to those structures if left in the ocean. As Andrew mentioned, we've got some wonderful panelists, so I'm going to introduce them one by one and give them a brief moment a few minutes to talk about their involvement in the NDRI research and what they're particularly been focusing on. And then we'll all come back in to discuss some of the broader questions. So first up is a project led by Professor Rob Melchers from the University of Newcastle and Professor Mike Tan from Deakin University. They are working on developing a tool for predicting the lifespan and corrosion behaviour of decommissioned oil and gas metallic infrastructure in the ocean. And Rob, I might throw to you first, please, to deliver your introduction.
Yeah, thank you very much. As you've already heard, the idea is to develop a tool, but in a sense, that really means something like a model or some equations that you can use to predict what's going to happen to your mainly steel infrastructure in the ocean. We've been working on this topic for a long time, including for pipes, mainly in the North Sea in that case, and it's a strenuous and a long-term project that we've been working on, and we're sort of keying into that with this. Now, you've got to remember, models or predictive tools have got to be based on data, and data is very hard to come by. We've gathered data from all over the world over a long period of time, and we've used that, in essence, to try and develop some models. And the first thing you've got to get to terms with when you're talking about corrosion is there's no such thing as a corrosion rate. The rate varies with time and as the object corrodes further. So in this case, we're really talking about long-term corrosion. And fortunately, if you leave out what happens in the first 2 or 3 or 4 or 5 years, the long-term corrosion is roughly linear. It's not quite. We now have data, not very good data, but we do have data going up to about 600 years of exposure gathered from archaeological objects and so on, and that shows that it's distinctly non-linear. But it's not that non-linear. For the first 100 years or so, which is probably all you guys are going to be interested in, it's pretty linear. The information we have covers immersion corrosion, it covers tidal, intertidal zone, it covers the splash zone, it covers the, if you like, the atmospheric zone right above the water. So there's a fair bit of information. The problem with this project is, in a way, that what we already have, how does that relate to what happens in WA and what happens offshore, and how does that relate to Bass Strait? So we need to do a calibration exercise, and that's one of the reasons we've been saying to the industry participants, please supply us with whatever information you have for the longer term observations. And then we can relate that to the climate issues. For example, the most fundamental issue in terms of corrosion is the average water temperature. If it's low, there isn't going to be much corrosion, obviously, and if it's high, there's going to be a lot. But there are other issues, for example, microbial corrosion effects, which depend on the supply of nutrients, for example. But that may not be an issue if you're a long way away from a platform. So we need to look at things like water quality. And in the end, what we're going to come up with is either a series of graphs or some equations that represent those graphs that you can plonk in the various parameters that we're going to suggest that you measure, and then you can predict how much corrosion is going to occur over a period of time. That's fundamentally what we're trying to do here. Mike will talk to you about, no, I should say, first of all, most of the work we're doing is on, if you like, plates or large objects like tubes and so on, without looking at the fine detail of the construction. But in the pipes, typically you have flanges or welds, or you may even have laps, and they cause some very specific problems, typically more corrosion. We know already from the North Sea work we did a while back that circumferential welding is a problem, and longitudinal welding of tubes is an issue where there's more corrosion. And if you're interested in perforation, the idea of pitting corrosion becomes important. But if you've got nothing in your pipe and everything is completely clean and the pipes have been capped before you let them go, there shouldn't be a problem. But again, that's the sort of influence and the sort of criteria we have to put up in terms of our final report. That's probably sufficient from what I have to say. And I'll, through you, I'll hand over to Mike.
Okay, thank you, Rob. Yeah, it's a very nice introduction, and you know, you have worked on this space for a long time, as I mentioned. You got a lot of data, but gaps, you know, in the data we have at the moment. As you mentioned, you know, the infrastructures or pipelines, they may be uniform. They are not actually clean. You know, we have, for example, we have like some areas with some crevices. For example, the jackets and some food joints or the wraps. You know, when you lift the pipeline or structure in the ocean with this type of structures, you will leave some crevices or like heat-affected zones, sediments. They are not uniform. They create some uncertainties, and in terms of the biological activities, corrosion, localized corrosion, crevice corrosion, pitting corrosion. This type will come into the equation. So what we are doing, my team at Deakin University in the past, we mainly work for the oil gas pipelines, which is like in the underground oil gas pipelines. You know, we have working with the energy pipelines, cooperative research center, future fuels research center. We mainly work on what happens pipeline buried underground. But for this particular project, we actually use some of our monitoring devices, monitoring techniques to simulate the situation. If you have a crevice left on the surface, what's going to happen? It's going to have what sort of corrosion rates, yeah, and what sort of initiation and propagation processes we're going to experience. Because these are important, because these areas could be actually causing your structure to collapse, because these can have a much higher corrosion rates than what a general model can predict. For example, Rob, your model, you basically predict a general trend over a long period of time, but at certain locations and a crevice, you can have a much higher corrosion rate. We have done some preliminary experiments in Victoria, Queenscliff. We have put some probes in the ocean. We found the corrosion rates can up to like 8 millimeters per year under the crevice, but almost zero on other areas. So what we are doing is basically to simulate some of these with the critic situations to produce data which can be used for the models. We can instead of the prediction is a straight line, we can a region. Yeah, you can say what's the highest possible corrosion rates, and what is the average, what's the general corrosion rates. So in that way, we have a better idea about some of the critical corrosion situation happening. We have put the probes in Victoria, and we're also going to put on Newcastle. So we compare the results and the situations. So basically, that's what we are contributing to this project. Thank you, Tom.
Thanks, Mike and Rob, for that great summary of the work that you're doing. Again, it's really interesting to hear that there's such a range of factors that impact corrosion. I think that's going to be very similar for a lot of the discussion that we have, is the environmental parameters, the water quality parameters are really key to all of the things that we're going to be discussing in this session. Next, I'd like to introduce Dr. Ebukan Olawai, who is from the Curtin University Corrosion Engineering Industry Centre. And Ebukan is working on the project entitled An Investigation into the Degradation of Non-Metallic Components of Oil and Gas Infrastructure in the Ocean. Ebukan, if you can give us your introduction, please.
Hi, Tom. Thank you for the introduction. So to recapitulate, I'm Dr. Oluwaye from Curtin Corrosion Centre here in Perth, being from Western Australia. So the title of the project we're working on, as Tom said, is an investigation into the degradation of non-metallic components of oil and gas infrastructures in the ocean. So here we conduct research into the kinetics of polymer degradation. First, I want to acknowledge the team, including Associate Professor Suarez and Professor Ianuzzi from Curtin Corrosion Centre, as well as Associate Professor Higgins from Curtin Oil and Gas Infrastructure Centre. So our prime objective is to provide a clear understanding of the fate and degradation of non-metals, basically synthetic polymers such as protective coatings used in oil and gas infrastructures during decommissioning. So far, for the past 6 months, we have reviewed all the relevant data in the broad literatures. So not all the data in the literature are actually useful, because most of them are actually conducted for commodity plastics, which are also limited to surface of the ocean. So also, we have estimated the changes in offshore parameters. By changes, I'm referring to attenuation of light intensity, variation in temperature as you go in depth, pressure, chemistry and biology of the marine conditions, for instance, in the northwest and the southeast region, as well as the geometry of the infrastructure itself and their relative effect on the degradation rate of non-metals, particularly synthetic polymers. These parameters are very important. Why? Because they detect the initiations, pathway, as well as the chain branching reaction of a polymer. Anybody in the polymer science, we know that reaction mechanisms for polymers are mostly dictated by radical reactions. So light intensity, temperature, and pressure play important role in all those pathways. I believe I will have a chance to talk more about the mechanism or the pathways later. However, all this has allowed us to develop a robust model to assess the lifetime of this material during decommissioning, as well as to predict the formation of degradation products. So by degradation products, I'm referring to dissolved organic carbons, dissolved organic nitrogens, CO2 in the form of carbonates, as well as debris such as microplastics, and their relative sensitivities as a function of depth. So all these parameters, their relative role would vary as you go in depth and marine depth. So we have carried out some sensitivity analysis to actually regulate or to understand the role of each of these parameters. Because in the end, we want to be able to answer the question, how long will it take for this material to disappear in offshore environments? Thank you, Tom.
Thanks, Ebukan. That was a great introduction. And our fourth panelist this afternoon is Associate Professor Stuart Higgins from the Curtin University Oil and Gas Innovation Centre. And Stuart's leading the project on risk-based marine impact assessment of naturally occurring radioactive materials, or NORMS, and mercury from decommissioning oil and gas infrastructure. And Stuart, if you can give us your introduction, please, into the work that you've been doing.
Hello, thank you, Tom, for that introduction. So I'm the leader of Project 2.3 and 4, and although I have a fairly extensive oil and gas facility and subsea engineering background, my background is certainly not ecotoxicological, but I have a very good team supporting the project. So putting it as concisely as I can, the project's aim is to enhance the understanding of the ecological risk posed by norm and mercury contaminated pipelines to support science-based decisions on their decommissioning. We're currently 50% way through a 2-year project, and the project is actually a collaboration between the Curtin Oil and Gas Innovation Centre and UK's National Decommissioning Centre located at the University of Aberdeen. The skill sets of the team include 2 ecotoxicologists, Dr. Darren Copel and Dr. Rebecca von Helfeld. We've got a chemical engineer, Dr. Fenny Crow, who specialises in mercury measurement and partitioning, and Dean Crouch, who specialises in industrial norm measurement, both offshore and onshore environments, and Dr. Astley Hastings, who is the University of Aberdeen lead and is an environmental specialist with extensive oil and gas experience. Aberdeen have been primarily focused on the mercury side of the problem, and here at Curtin, we've been focused on the norm side of the problem. I think importantly too, we're also linked with ANSTO and the Norm and Mercury team, actually run by Tom Cresswell, and we're sharing the learnings, ideas, and providing complementary experimental and desktop effort to achieve a better understanding. And we do not want to unnecessarily duplicate the work, so we're actually collaborating and working together, which has been fantastic. So what are the contaminants? Where do they originate, and where do they fall in oil and gas systems? So norm is a naturally occurring radioactive material. Its source is thorium and uranium, which occur in a reservoir. Uranium and thorium are generally not soluble, so they don't readily migrate into the production system, but radium-226 and 228, created through their various respective radio decay chains, do and are soluble, and they have a half-life of a wide range of between 1600 and 5 years respectively, and they're transported through the production system and can participate as barium sulfate, calcium carbonate, calcium sulfate, and that scale adheres to the inner walls of line pipe and production equipment. And the radium in these scales will actually decay and ingrow radionuclides in their respective decay chains. There's also other radioactive isotopes. Radon gas is also produced in the basin and gets separated with gas and condensate systems. Radon-222 has a very short half-life of 4 days, but does decay to form lead-210, which has got a 22-year half-life, and polonium-210, which has a 138-year half-life. These decay products themselves can also form as films in pipe wall. So in general, at a very, very high level, you could say that radium scales are found in pipelines exposed to multi-phase well fluids, while lead-210 and 210 and polonium-210 are found in gas export systems. There is a further complication. There's a phenomenon called radionuclide ingrowth, and it has the potential to complicate the assessment of risk, because what you actually measure as a radiation activity at the time of production cessation can actually increase. In the case of radium-226, this is by a factor of 8, and the timescales we're talking about are many thousands of years until the equivalent levels of activity are at the point of when the scales are formed. So in summary, the spatial and temporal distribution of norm is complicated. It is very difficult to measure in situ, but the timescales are significant given the degradation rates of the contaminated pipelines. And so it's potentially anything beyond 100 years where you may start to see breakthrough of seawater exposing the marine environment to radium-226 and its decay progeny. That's where it becomes an environmental issue. On the other hand, mercury also emanates from the geological formations that is produced in various chemical species, which depend on pressure, temperature, chemistry of the formation in fluids. The main species are elemental ionic compounds, such as mercury chloride and sulfide, and the organic, such as methyl mercury. All these species can accumulate inside production systems by multiple processes. And you know, elemental mercury can condense on the surface of a pipe. It can also absorb onto the steel surfaces. And also we have an absorption of elemental mercury and mercury sulfide into the actual corrosion products on the inside of a pipe. From a decommissioning perspective, the latter two are the most important of the primary interest. Methyl mercury does exist in production systems, but along with the condensed mercury, it can be extracted through flushing. So the primary concern is really, although elemental and mercury sulfide, unlike norm, they don't have a decay characteristic, but there is a potential when they're exposed to the marine environment to transform by oxidation and methylation to bioavailable methyl mercury, and that then poses a direct and bioaccumulation toxic effect to the marine environment, the sediment organisms, and potentially humans via the biotrophic transfer. In terms of our scope of work, we're focusing on the characterization of norm and mercury contamination products in oil and gas pipelines, the ecosystem receptors around the pipelines, whether they're in the sediment or in the water column immediately above the epibenthic or higher, the exposure pathways to these receptors, and the associated quantification of impact, whether that be biodiversity, bioaccumulation, or toxicity of the contaminant. On top of that, we also need to address what is the appropriate risk framework to assess this multifaceted and very complex and in the future problem for a contaminant that has spatial and temporal variability. We're not investigating specific case studies, but are using a generalized case of contaminated pipeline left in situ on the seabed to develop an understanding of the processes and key parameters which can subsequently be used for site-specific decommissioning scenarios, whether that be in the Gippsland, Carnarvon or Bonaparte basins. So over the last 12 months, our first milestone, we delivered a very literature review consolidating and critiquing the public and available grey literature, which there is a paucity of. Through this process, we've identified the current understanding of risk that norm and mercury pose to the marine environment from decommissioned oil and gas subsea infrastructure. We've established what we believe to be the key knowledge gaps. And in summary, I've already mentioned it, there's a paucity of data describing what concentration of mercury level or level of mercury and norm and the forms found in oil and gas infrastructure, and whether they are harmful to the marine ecosystem. Most ecological risk assessments have contamination to measure, but we are identifying predictive lines of evidence to assess their potential impact. There's very little published in the way of inventory of contaminated products, the form, the species, the mass, the distribution in pipelines, and this applies to not only the operating condition, but the cessation of production or following any cleaning operations. We don't know how the speciation and distribution of contaminated products in pipelines affects important environmental transformations, controlling the exposure pathways, whether it matters in the timescales of 100 years or 1,000 years and beyond. And importantly, we don't know in detail how the different environmental conditions, either within the seabed, on the seabed, above the seabed, affect the contaminated products and the transformations and the resulting mobility and bioavailability. And in terms of the measurement tools, we don't know specifically what needs to be measured for ecological risk assessments. And we also have a very poor understanding of the current and future technology options for measuring in situ mercury and norm contamination. So over the next 12 months, we plan to develop an ecological risk assessment framework that hopefully can generalize to all contexts, but provide the flexibility to tailor an assessment to a case-specific context. So this is really about pushing our current desktop level understanding using what we've learned from the literature to populate a best practice risk framework to identify and prioritize what needs to be done in the next phase of the research, which we believe will be experimental as well as analytical. And we hope to more openly collaborate with others and have better data access. So in brief, we're now developing a set of pipeline contamination specific management objectives to meet legislative requirements and provide the means to assessing ecological risk by a weighted evidence approach. This aligns with the best practice of the ANZG water guidelines, quality guidelines. We're also investigating and looking more detail into the important environmental parameters and factors controlling contaminant exposure pathway and hazard impacts. And this will be used to develop our risk framework. And finally, we're identifying the technology options for in situ measurement of mercury norm and the technology readiness level. We've been in contact with more than 15 technology providers internationally, and there are potentially 10 of those technology providers which have the potential ability to measure in situ norm and mercury. And that's a very brief summary of what we've been up to.
Thank you, Stuart. I think, yeah, very good overview, and especially your comment on the, we have lots of known unknowns in that contaminant impact space. I certainly echo from our research group side and what we're looking at. I think everyone in the audience as well will understand the linkages among these three projects in terms of how different structures corrode and behave in the sea in the long term, then influence the potential release of any contaminants and or vice versa. And then as well, the linkages with the other projects discussed earlier this morning about what ecological systems and organisms, either native or invasive, inhabit the around these structures, then really influence what that risk may be from the corroding infrastructure and associated contaminants. So thank you all for great introductions. I guess I might start with Robert in terms of what do we know really about how structures break down over time in the marine environment. Rob, what are those key factors that are really influencing degradation, and what do we know about what happens to a structure over that really long term?
Well, if you look at any piece of steel, and it doesn't actually matter precisely what the grade of steel is, I might make that point right at the beginning. There seems to be this sort of feeling that, oh, we change the steel and we're going to get much better results. Even with stainless steel pipes, for example, you're not going to get much better results. So it's not actually so much the material that's an issue, but the environment. And as I mentioned before, it's typically temperature, and what you tend to see is that the stuff corrodes, you build up rust layers on it, and they build up over time. And that if you're talking about the atmosphere, then often they spoil off again, or at least some of them spoil off. So you delay the whole process. But generally speaking, particularly in the immersed condition, which is really of most interest for pipes and the sort of things we're talking about, the rusts build up. They look brown, perhaps sometimes red, sometimes black. It depends precisely on the conditions. But typically speaking, if you're talking about oxygen-rich environments, you're going to see red-brown type rusts. But over a period of time, and let's assume we're in an environment a bit like here in off the coast here in Newcastle, where it's 20 degrees C on average, after about a year or so, things start to slow down. And then suddenly, if you keep looking over a longer period of time, the rusts also start to change. If you peel them off, then underneath the rusts, next to the metal, you start to see a lot more black material. And you see in there things like magnetite, and if you're really good at it, you can identify hematite, for example, and you can identify some various things called green rusts. But they're all great for scientists, but for the engineering profession and the people trying to predict how much corrosion is going to occur, really what you want to see is the amount of metal loss. And typically you're going to see pitting. And you can see, unlike what's in all the textbooks, which is an isolated pit surrounded by a whole lot of cathodic area, what we tend to see is fields of pits, just whole undulating areas over relatively large areas, like could be 10, 20 square centimetres, for example, where that occurs. And that can peel off under certain conditions. So it depends. If you've got a lot of impact on your pipeline, for example, or you have erosion, that'll change the system. I didn't mention that before, erosion, but it is an issue if you're in sandy soils in particular. If you're on rock soils, if your pipe gets knocked around, well, that might knock the rusts off, and then you lose this protective effect. So that's broadly speaking the way the process works. And the important part about that description is that you have early, very high rates of corrosion within the first few months, say, then it gradually slows down, and then it picks up again. And what that tells you is that the underlying corrosion equations or chemistry actually changes. It changes from straight out oxidation to where the electron acceptor changes to the hydrogen evolution reaction. And that's often not understood. But that means that the long-term process is not actually governed by oxygen at all. And that's why you can have long-term corrosion in very deep waters where there's virtually no oxygen or very low oxygen levels, and yet it keeps going. And if you, for example, look at the Titanic, where there's been some studies done over, say, 6 years or so, it's still corroding. And it's been in there since 1912. So there is a long-term process, but as I pointed out before, it's not linear. And we need to understand that if you're really interested in long-term business. I was asked quite a few years ago about, oh, well, how long will it take for our pipelines to corrode away? This wasn't by you guys. This was a completely different question from a completely different source. And it's like, well, it's going to take a few hundred years. And they didn't like that idea much. Now, but it does mean that if you are looking at pulling the pipes out off the seabed, you've got a fairly long length of time before serious things happen, unless you're close to offshore platforms where there's a lot of pollution and you're in relatively shallow waters. Then things start to become much more difficult. And we have some information about that, which will be in our final report, but it's to do with microbial corrosion. And one thing we do know from, not so much from the Australian operations, but from international operations, that typically around offshore platforms, there's a lot of material that falls off or shouldn't be on the platform, or we just get rid of, and that actually causes problems with change of the water quality, and in particular, the presence of dissolved inorganic nitrogen. That is a real issue. The problem, we know that in particular from the work we did a while back on the North Sea, where we were looking at injected nitrogen for controlling of the hydrogen sulfide coming out of oil wells. They wanted to control that, and one way of doing that is to pump in a lot of inorganic nitrogen to let the nitrogen-loving bacteria outperform the sulfate the hydrogen sulfide-producing bacteria. But it actually caused a lot of problems with their pipelines. They were corroding a lot more inside than they had anticipated, and it was because they were actually spoiling it for themselves, right? So I'm not sure whether any of this is relevant to Western Australia or the Bass Strait, because it depends on these water injection pipelines. But it does show that the water quality part can be really, really important, and that you can only gather that by looking at the pipeline that's on the ground in the ocean and looking at the environmental conditions around it. Just taking a generic view isn't going to get you the answers. I hope that helps a little bit.
Yeah, look, thanks, Rob. I think again, that's bringing up the complexity of the issue. And I think a good segue to bring Mike in. You mentioned in your opening address, Mike, that you know, some pipelines are degrading up to 8 mil per year, depending on the pitting and the conditions. So what are those key environmental variables that are really influencing that sort of very specific degradation, and how does that relate to the differences in water quality that we've got around the different Australian locations?
Yeah, thank you, Tom, and thank you, Rob, for your good points you just made. I fully agree. You know, in terms of general corrosion is an electrochemical process. You know, is generally say whatever the parameters, you know, influencing that electrochemical process or the influence corrosion. Obviously, like oxygen level, like bacterial activities, because they generate the chemistry for corrosion to happen. So that which has Rob has mentioned. Of course, that depends on what is the situation, which factor is more important and contributing more to this process. But in general, as Rob you have mentioned, as a general pipeline, if you look at big picture, the models you have developed over the past 20, 30 years, you know, is way now, and you know, this is a good indication about what's going to happen in terms of the rusting of a pipe. But for the decommissioning of a pipeline or influx structures is one issue which you know, is critical, which is not necessarily the whole structure is rusted, is consumed. The many cases is because what is the time the structure is going to collapse. You know, the pipeline is going to break down. Many cases, this is quite important, because once it starts to happen, then your structure, you know, we influence a lot of things like the environment. Okay, so and the most important factor influence the time for the structure to collapse can be due to localized environment and localized corrosion, we call that. The most, that's why we, in the research project, Rob and I, we had discussion, we have identified 4 cases, 4 factors we consider critical for the industry to know. One is the situation when we have a crevice, exists, like a wrap or through the joint or like the jacket, you leave a small crevice. That is the area bacteria like to grow, and that is the area crevice corrosion is going to develop. They create a very sensitive location for corrosion to grow quickly. We had some initial experiments in Cresswell. We detect about 8 millimeters per year of corrosion under this crevice. But outside it can be 0. You can, the whole structure, you almost not see much corrosion, especially if you have cathodic protection applied. You don't see anything, but that crevice area, you can get a lot of corrosion. And that area can be critical for the structure to collapse. So that is one thing where we want to find the data. There are very few data, very little data available on that, because this to get the data and this situation is not easy, and that condition changes. As Rob mentioned, if the water is contaminated, temperature changes or depth changes, you can get different results. That's why we don't need to collect data from monitoring and in order to make a model prediction more realistic. Another situation of concern is, as Rob mentioned, is the pitting. So in that case, in that particular environment, is the pitting going to be a bigger problem, and what is the rates of the pitting corrosion is going to happen? That's also data is not always available. Another issue is like the weightment, the joints, there's a heat affected zone, there's a weightment. So is that a bigger problem? Can cause a much higher corrosion rates than other areas or not? And we don't expect so. Yeah, from the corrosion electrochemical point of view, we don't expect that can happen. But we don't know. There are not seems there are insufficient data to back that prediction. So what I say, I add to what Rob has mentioned. What I mean is the structure design and some localized environment can contribute to the corrosion behavior, corrosion rates, and it can influence a lot significantly on the prediction. So that's to say, I want to bring these issues into this space for discussion. Yeah. Thanks, Tom.
Yeah, thanks, Mike. Ibukan, just keen to get your thoughts on, we're talking quite a lot about metals and degradation, and again, it's a very complex answer to the question of how, what are the main factors? What are the main factors for you with the non-metallic parts of the infrastructure that influence the degradation of that, of how that structure breaks down? You mentioned light availability, especially for polymers. Are there any other key factors that you identified that influence that breakdown, and how do the key factors differ depending on which basin you're looking at?
Thank you, Tom. So if you're talking about synthetic polymers, in addition to the influence of temperature, you can have photochemically initiated reactions, which you've already mentioned. Also, you have the hydrolytic pathway. So with the water itself can also initiate some degradation in the material. And as you go down in depth, of course, temperature will decrease. So the influence of temperature will decrease. The influence of light intensity will decrease because you have solar attenuation. For instance, below 50 meters, you have cutoff of UV. So those impacts will relatively decrease. However, for hydrolysis, it's actually increased with depth because it's actually being driven by hydrostatic pressure, which we all know that it increases depth. So yeah, so those are the 3 main, I can say, chemical pathways. You have the biological effects as well, such as microbial degradation, as well as mechanical pathways. For instance, if you are dealing with infrastructures at the surface, yeah, abrasion due to wave may be important, but if you are going considerably down in depth, wave will have relatively no impact, but rather marine sediments, for instance, sands flowing in the water column may actually induce some mechanical abrasion. Now, what impact, or how can you quantitate the impact of these key variables? So I would say principally one parameter dictates all, which is the depth. So once you can, the depth is what is dictating how much light intensity you have, the depth that is dictating the temperature and the static pressure and the chemistry and the biology of the water. So to me, the most important variable will be the depth, which detects other variable. Then we can actually couple all this into one simple information to predict or to model the degradation. And as you also had, one key difference between that and META, Rob and Mike have mentioned scale of millimeter per year. In terms of polymer, you're talking about mostly, depending, especially those used for protective layers, you are talking about micrometer per year. So they are much, the rate is much relatively slower compared to metals. In fact, that's very reasonable. That's why they are being used as a protective coating in the first instance. And as I mentioned earlier, the reaction is mostly driven by radical reactions, which is the presence of unpaired valence electron. Of course, there could be interplay of ionic interplay. You may have an ionic interplay from the environment, but that is of a relatively low impact. So if you can control, what we need to know is at a particular depth, what is the temperature, pressure, light intensity, the chemistry, and the biology. So that we should be able to get a reasonable information of the degradation of the synthetic polymer. Thank you.
Yeah, thanks, Ibukan. Stuart, I'm going to pass to you the question around, are there any key water quality parameters, so physical or chemical, that you've found in your research looking at driving then the potential risk factors for the contaminants that may or may not be in this production infrastructure? So are there, the presence of oxygen or light or salinity? What are those key things that, again, are there key factors that industry should be looking for when they're looking at degradation to also then inform potential risk to from the contaminants perspective?
We have investigated just recently some of the geochemistry of the environment on the primary contaminants of concern. The majority of which that we've looked at don't appear to have an influence, but there are some that most definitely do. And as you mentioned, oxygen content is one of them. In oxic environments, certain transformations happen with a particular contaminant, and in others that may not be the case. And then you're looking at anoxic environments where a transformation occurs and a contaminant which may not be bioavailable all of a sudden becomes quite soluble and is bioavailable. So we think, yes, so oxygen levels are important. Organic matter content is also important, and also the type of microbes that are present also. And probably the biggest uncertainty is actually lay in the sediments, and so we're just recently looking at that, and so our primary contaminant of concern, radium sulfate, is not necessarily it's not very soluble, but if, for example, and it wouldn't be particularly soluble if it's sitting on the seabed, but if it's in the sediment and in an anoxic environment and there's microbial activity, then that may well be, you end up radium being released and then being bioavailable to any of the organisms that are in the pore waters of the sediment. So then it becomes, then it does actually become an issue. So yeah, I think I've captured most of the parameters that we think are important, but we have very little data about, and we're struggling to quantify.
Yeah, thanks, Stuart. I think I'm gonna try and get onto the data availability and gaps a little bit in a moment. But I first want to just touch on some questions that I had earlier and some questions that have come through from the audience around biofouling. So again, through this morning's discussion about the ROV images of encrusting invertebrates and organisms that inhabit these structures as the start and the foundation of that artificial reef that then attract a load of other organisms. How does the influence of biofouling impact the degradation rates of both the metallic and the non-metallic components? And I might start with you, Mike, as to what your thoughts are on that one.
Yeah, thank you, Tom. I think biofouling is a type of microbiology or biological organism growth. If it produces some sort of local environment, especially acid, that happens. That can cause two effects. One is to generating a corrosive environment, which is you have acid. Another effect is it can create some sort of crevice on the surface, which there's a type of corrosion called crevice corrosion that is specifically relevant to this type of situation. Yeah, we would expect the corrosion is going to grow, increase most cases. Depends on what type of microorganism, of course, and also the conditions. Yeah, what do you think, Rob? I think you have more experience on the ocean.
Thanks, Mike. Look, I agree with what you're saying, but I think in context, all that's true for relatively short-term exposures. If I compare to microbial influenced corrosion, most of the research that's been done internationally has been in laboratories for, say, 6 months exposure, and they find that bacteria XYZ is really corrosive. But if you stand back and say, well, what did we learn from long-term observations in the ocean or in harbours? There isn't that much evidence that biofouling makes an enormous amount of difference. What tends to happen, if I can scale it up, is that the curve goes up, but the actual slope doesn't change very much. At least that's our impression at the moment. And I agree that the data that's available is relatively scarce, but if you just stand back and take an overall look, there isn't really all that much data that would suggest that the long-term corrosion rate is significantly affected. Short-term, absolutely. It makes a lot of sense in terms of the pH and so on that you're talking about. But if you already have lots of rust on the surface and the hydrogen evolution reaction ultimately controls the long-term rate, then I don't think it's going to be an issue. But as I said, the curve moves up, but the long-term slope stays more or less the same.
Yeah, thanks, Rob. Ibrahim, from your perspective on the non-metallic side, how does that biofouling that is going to be present to differing degrees in different waters, how does that impact rate of degradation of the materials you've been looking at?
Yeah, thank you. So basically, we're talking about two things here. So you can have the microbes. Also, you can have the microfoulants, such as barnacles, attaching to the surface. One thing I can tell you for sure is they will definitely actually enhance the degradation for non-metals, for synthetic polymers in this case. Why? Because of the enzymatic activities that such organism actually constitute to. So yeah, for non-metal, yes, they will contribute, but the contribution is also, it depends on the perspective you're looking at it. So it's not going to change the micrometer per year to millimeter per year. No, it's still in the broad concept of the micrometer per year, but relatively, yes, it's increased, but not relatively large, in a large amount compared to what it is actually. Thank you.
Yeah, thanks, Ibrahim. Stuart, I'm going to come to you in a slightly different topic, but you touched on in your last response. And what are those real key things that we don't know? You know, you mentioned that you've gone through the available academic literature and the available grey literature. What are the key things that we don't know about contaminant risks, mobility, transport, impacts to receptors around the structures, and you know, if you could prioritize those key things, where should we really be looking further into that?
That's a big question, Tom.
You've got a couple of minutes.
I suppose we are approaching this there are so many details and layers you could get to really understand what's going on, and we're trying to get at a level of understanding where we can put all this together to work out conceptually what is required and what's missing to give the answers. So, you know, and I'm not an ecotoxicologist, but in terms of what Darren and Rebecca are looking at, you know, there are published guidelines and reference values that you can apply, but they are by their nature general. And so when we're trying to assess the risk, or when the operators are going to have to assess the risk for a specific case of a pipeline sitting on a seabed that's contaminated with normal mercury, there's going to have to be a far better understanding that we can currently gain from the literature in terms of the exact organisms that are living in the benthic community, what's sitting underneath and around the pipeline, as well as far more detail on the organisms that are sitting on and above that aren't necessarily, you know, photographed in the current ecological surveys that are happening. But we do understand, as I said before, some of the key parameters we need in terms of understanding how the contaminants that we do know about, how they can be transformed and made bioavailable. But then you've got the whole exposure and then impact assessment, where you need some very specific details about the way specific organisms react to exposures from radiation, both internally and externally, and then dealing with the whole bioaccumulation toxicity side of the organisms as well. So that's not a very specific answer.
That's okay, because I'm aware of the magnitude of the task ahead. But
that was like, what was the meaning of life?
It's a look. It's a very good summary, I think. But again, it's important to draw out the fact, Stuart, and to everybody, that this really, you know, there are a lot of known unknowns in that specific contaminant case.
Can I comment on that?
Yes, please, Rob.
Because in a way, I can sympathise with Stuart, because in a sense, we were faced with a similar scenario 20 odd so years ago. I remember once asking a question to a whole lot of eminent corrosion scientists, well, what about the effect of temperature? And I was like, oh, go away, Sonny, we can't work that out, it's too difficult. And yet, if you look at the data properly and you start to think about some of the fundamentals, you can do it. But the issue is that you have to go around in circles. So you look at data, you look at the fundamentals, you look at the data again, and it's an evolving process and it takes a long time. So to expect results within a few years, I think, is being optimistic. We're still learning about things that we looked at maybe 20 years ago, and we suddenly think, now we begin to understand what's going on. So give Stuart a bit of leeway.
So yeah, exactly. I mean, you know, for example, on the mercury side, we know elemental mercury, you could safely sit on the seabed and in the pipe, but the key is the methylation. And as we're only just going down that path now, and we're looking at the geochemistry, the microbial transformations that could potentially happen to predict methylation. But as we understand today, there's no model that we can take off the shelf to predict methylation of mercury. It's all experimentally based. It's all been measured. So, and the problem we've got is that we have to project in the timescales that Rob's talking about. We have to project beyond the 100 years. We don't, to be honest, I don't think we need to worry about from 0 to 100, because we think the pipeline will be intact. But it's the 1,000+ years that we've got to project out to and forecast, and that's, for us, that is a real challenge. And so, you know, we're looking at food web models now where maybe we can attach, you know, a methyl mercury contamination into that trophic chain to see where it ends up. And we're just, as Rob, we're just sort of scratching at the surface, trying to understand the processes. We're going through a bunch of environmental parameters, temperature, pressure, salinity, just trying to work out, does that change the properties of these contaminants? And we're just churning our way through it. So yeah, some of it is important and makes big differences. And from what we can see, we can change a bunch of parameters and it makes absolutely no difference. So we're just on a journey at the moment.
Look, Thank you, Stuart and Rob, for chiming in there. Look, I think I'm conscious we've only got a few minutes left. I think we could certainly talk for another hour easily on all of the conversation pieces that have come up, and I've not even got through all of the questions that I wanted to ask. But in the final question, if you could each have a moment or two to answer. In the spirit of NERA and working together collaboratively, industry, academia, government, I want to ask, just get each of your opinion on, given the journey that you've gone through as part of this phase 1 of NDRI, what's your thoughts on whether we have, we as the community, both within the academic research side, the industry side, the government side, do we have currently the critical mass in resources? So do we have the research leaders, the skilled workforce, the sustainable investment, the data availability to really deal with trying to answer the questions that have been posed to you or that you've posed as part of this NDRI. Rob, I might start with you to answer briefly, please.
Yeah, I think for us, because in a way we're starting with a bit of a heads up already. We've been involved in this area for quite a long time. But I must say there are some interesting questions raised as part of this project, and Mike's working on some of those. Sure, us academics will always ask for more money, or always ask for more time. So I think that's fair, but I think on the whole, at least in our area, we'll be able to throw some light on some of the critical questions. The real problems are in the detail areas. Mike's talked about things like welds and laps and so on, but we're still doing some fundamental research here with ARC support, for example, of the interaction between different grades of sand, for example, and steel, which is important for what happens under a pipe and when the pipe gets buried. We've done a lot of work over a period of 10 years with Sydney Water and Hunter Water and the other utilities for pipes buried, steel pipes and cast iron pipes buried in the soil. And then we went through the same sort of process that Stuart's just talking about, but it required a lot of investment on the part of the water utilities. They spent $1 million or more over a period of time just on us. So I think we're getting there, and I think we've got a good start. Obviously, more is going to have to be done.
Thanks, Rob. Just in the interest of time, I might quickly skip to Ibukan and get your thoughts on answering that question of do we have that current critical mass in resources from your perspective of the non-metals degradation pathways?
Thank you, Tony. So from my own perspective, I would say the methodology and the approach, in other words, the science is there, right? However, some important information are still missing. For instance, our model, for sure, you can take this particular type of polymer and you can actually predict kinetically how it degrades, how it forms, dissolve organic carbon, dissolve organic nitrogen, and microplastic. We can even account for how those degradation products, call them intermediate species, also degrade into finer species such as carbonate. However, one could ask, what are the relative impact of those things? How long will they have a particular timeline to degrade? But within their degradation time frame, what are the impacts on the environment? Such information that I believe we need expertise in that area to answer such questions.
Yeah, thank you, Ibukan. And Stuart, just very briefly within a minute, I see you shaking your head when I asked the first question, but just your thoughts on that one briefly, if I may.
Well, I suppose, I mean, I haven't looked at this previously in my previous experience. So really, we've started since June of last year to build a team. And it was only then that I became aware of what ANSTO are doing in ANSTO's work. So not to belittle the great work you're doing, Tom, but you've got 3 researchers now that wasn't working in the norm space and contamination space over the last number of years, and now we're starting up here. So I'd say it is under-resourced and underfunded. I mean, we're trying to grapple with fundamental questions about just the risk framework. How do you actually assess the risk? What does the regulator really need to be presented in so that we can capture all this uncertainty and actually present a risk assessment that gives some good insights to understanding whether it's deemed to be at an acceptable level or not. And so not only are we as a team digging into the detail and trying to understand these very complicated processes, but we're also looking at the highest level, trying to work out how we build this risk framework together, what's best practice for doing that. So in some ways, we think we're also providing a means for these concepts to be discussed with the operators and the regulator to work a better way of being able to establish what the risks genuinely are, and then to be able to make decisions. So, you know, we're proposing, you know, management objectives now within that risk framework. We've just started the process. We've got a long way to go. And the access to data, I'll just get on another hobby horse here, because of the bogey word of mercury and norm, nobody wants to publish any information. And we're dealing in a confidential, confidentially restricted program, but even then we can't get information. So yeah, we're up against the wall. Now we've managed to find enough public domain information that's giving us enough to be able to get some insights, but yeah, it's sometimes you're beating your head against a brick wall, really. Thanks for the therapy, Tom.
Always a pleasure. Yeah, thanks, Stuart. And again, I think that's a really good summary. There is that there is a lot of work to be done in the space that all four of you are working in, and I certainly thank all of you for your time and efforts in working through with the NDRI, and again thank the industry participants for working with you. Again, it's a very complex issue. I agree, Stuart, especially when we're talking about things like mercury and norm. It's very sensitive as well. We mentioned in the first session about the societal and political sensitivities around certain things, and certainly the norm and mercury really hit that nerve too. So thank you all for your involvement in the program and for your involvement in this science symposium today. I've really enjoyed it. I wish again like I could have another hour to speak to you all, but that's maybe for the next time. So happy to bring Andrew back in if we can, please, Joey.
Thank you very much, Tom. I think clearly we barely scratched the surface of that issue. A lot of really interesting discussion around the complexity and interconnectedness between the metal degradation study, the non-metal degradation study, and how that informs potential impact of contaminants on the marine environment as well. Just wanted to say thanks specifically to Rob, Mike, Ibakan, Stuart, and obviously Tom as the facilitator as well. Again, I'm sure that the researchers are happy to have further conversations with those of interest, and NERA can facilitate those connections as appropriate. That's the end of the formal proceedings for the symposium today, and just by way of wrap up, a little bit of time to spend on where NDRI is going from here. We have projects variously wrapping up over the next 12 months. So Michelle's connectivity study is, we have a final paper for that. Chad's work on invasive marine species will be wrapping up soon as well. And phase 1A of Ibakan's non-metal degradation study will end towards the end of this year. Towards mid next year, we will be wrapping up Diane's habitat value work, the metal degradation study, and also the contaminant work. And that will bring us to the end of phase 1 of NDRI as it's currently funded. We are in discussions right now around phase 2 of NDRI, which is likely to run from 2022 in July through to 2025. We just closed an expression of interest on Monday this week, which was to look at developing a roadmap of research priorities and projects for decommissioning in Australia. So if we're looking out over the next 10 to 20 years, what do we think decommissioning is going to look like, and what do we think the projects will need to achieve to actually answer some of the key questions we're going to have over that forecast period. Down the bottom, ndriaustralia.org is the website for further information. So feel free to jump on that if you want to learn more. You can also contact us at info@ndriaustralia.org as well. So just a thank you, just to wrap up today's session. Clearly lots of speakers, lots of moving parts. So I just wanted to ensure that people were appropriately recognised. Obviously, a thanks goes to everyone who joined us for this session. We had 150 people register for the symposium. We've had a fairly strong contingent maintain their interest throughout today, and so thank you for staying on there. Obviously, thanks to Milton Love for joining us in the evening from California. Also the panelists, so Diane, Michelle, Chad, Rob, Mike, Ivakan, Stuart, and Ian. Significant thanks as well to our facilitators, Tom and also Peter. Thank you to AV Partners for supporting the tech. I understand we had some technology challenges earlier today, and hopefully we were able to adapt and you were still able to pick up as much as possible. There will be an HD recording of the symposium made available to people as well. So if you need to pass that along to any of your colleagues, you can do so. And lastly, just want to extend an enormous thank you to Samara at NERA and the communications team. None of this would have been possible without the extensive investment from Samara to ensure that everyone was plugged in and in the right place and doing the right thing at the right time. So thank you to Samara and the team, and thank you to everyone else. Just in closing, we are proposing to run a second Mentimeter just to follow up, just to see if any views have changed around this topic of the influence of structures in the marine environment. Not to get on Milton's bad side, but also the positive and negatives potentially associated with that from your perspective. So with that in mind, if you could go to menti.com, if you have an interest to add another data set to our collection, the code is 58468793. We'll leave this slide up for a few minutes just so you have an opportunity to plug that number in. But for now, from me, I'd like to just say thank you to everyone for your participation. Thank you for your interest and look forward to speaking to you soon. Okay, goodbye.